Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process given by Dr. APJ Abdul Kalam, who says, if you want to shine like a sun, first burn like a sun. It is really very interesting and important statement. Let us recall in the last lecture what we learned. In the last lecture, we basically initiated discussion about the processes involved during a generic solid propellant combustion. We have seen that the processes involved in the solid propellant combustion is quite involved because of fact that there will be a gas phase reaction along with the solid phase, and even sometimes the liquid phase also will be involved in that. So, therefore, it is quite complex. Beside this, all three modes of heat transfer, namely conduction, convection, radiation, are also will be involved interchangeably. And the gases produced due to the decomposition of the propellant will be flowing over it, and as a result the velocity will be quite high, it will be turbulent in nature. As I told, there will be two phase flow, it is basically three phase, liquid droplets will be there, solid particulate will be there, and so also gas. So, beside this there will be also the, as I told, condensed phase reactions, and the processes are quite complex in nature. And to determine the regression rate or the burning rate from this mechanism is quite complex. So, of course, that we talked about a generalized processes involved in that, which is yet to be explored and understood fully. And later on we moved into the double base propellant, in which we have seen various zones of the during the combustions, and some of the important zones are fizz zone, foam zone, and dark zone, and combustion zone or the flame zone. Beside this, there will be also preheated zone in the solid propellant itself. And note that we looked at certain reaction in the dark zone, which is in which the temperature will be remaining constant, and this zone is also known as preparation zone or incubation zone, you can say, and which will be preparing the certain composition which will be participating in the main flame, and so that exothermic reaction can take place, and that will be giving the heat, supplying the heat to the solid surface of the propellant. And today we will be discussing about the composite propellant combustion. Basically, the processes involved during the composite propellant combustion is quite complex, because of fact that the composite propellant will have fuel oxidizer and also various additives which will be retaining their physical boundary, unlike the double base propellant where the fuel and oxidizer will be located at the molecular level. In other words, it is a homogeneous propellant, therefore, it is likely to be simpler one. But in case of composite propellant, it is heterogeneous in nature, therefore, the combustion processes will be quite complex as compared to the double base propellant. Let us look at what is happening, and before considering that, you can see that the composite propellant will be having a coarse oxidizer particle which will be crystalline in nature. There will be also fine particulates, and there will be binder which is the base on which these particulates are embedded in. And note that these things are very important, and we are not considering the other additives in this. And if there is some initial ignition energy, let us say some heat being transferred towards this process, this is the heat energy due to ignition, and when it is coming to this over here, then what will happen, this oxidizer will be decomposed, so also the binder, and then this will be producing the product, and then the products will be reacting with each other, and then maybe there will be a flame will be formed during this process. Let us look at how does the flame look like in a composite propellant combustion. So, if you look at this is your basically propellant strand, and this is your flame which is being located in this. This is your basically a flame surface, and that is supplying the heat to this propellant burning surface. This is your propellant burning surface, and the heat will be transferred from this surface to the propellant, virgin propellant grain. Heat transfer takes place due to heat conduction, and that is known as this portion, you can call it as a preheat zone, and this is being regressed, and then as a result there will be a foam layer. You can see this is basically preheat zones which is being shown here, and there will be bubble will be formed and some gas will be released, so that this portion is known as the flame foam zone, or this region, you can consider this region is basically known as the foam zone, where it is some bubbles are being formed. And of course, if you look at the temperature profile, will be looking like that. There is a little increase here, and then of course, it increases due to the flame, and then it reaches the maximum values. This looks to be quite simple in nature, but keep in mind that as we know that there will be binder, and binder means basically the fuel, and AP crystal, these are crystals. There will be ammonium percle flame, there will be some gases, and then there will be granular diffusion flame, one can look at it. But if you look at the various models have been proposed, and one of them what we are going to discuss, basically a single crystal I can take here. This is the things I can take. This is the crystal, single AP crystal, and this portion is your binder, this portion is your binder. So, that we are taking, this is your binder and this is your AP crystals, and when it will subjected to heating from the flame or from the ignition source, it will be undergoing the decomposition, pyrolysis and gasification. In the beginning it may be endothermic in nature, but later on when there will be adsorption of the some of the species, it may be little bit exothermic in nature later on when the flame is established. Then when it decomposes, that will be forming a flame which is known as ammonium percolate flame, and these are the also the fuel will be decomposing. So, this is known as fuel products, fuel products which will be forming on the both the sides, and this ammonium crystal is basically flanked with the binder. And some of the oxidizer which will be not participating in the combustion, it will be going away, and then final diffusion flame is being formed. And we will discuss little bit more about in the next slide. And this is the model was basically given by the Beckstead, Durr and Price to estimate the burning rate and also look at how the combustion process can be incorporated in the model for the burning rates and other structure of the flames and temperature profile predictions and other things. And of course, there are several models which are available, but this looks to be capturing the physics of the problem. Therefore, we are considering here that is in literature known as BDP model for composite propellant combustion. So, as I told that the ammonium percolate crystalline, the particles, right, is being flanked with the binder. We are taking a very small portion of that, and when the heat is transferred due to the initial ignition energy or some other energy sources to the surface, both the binder and the oxidizer gets decomposed. As a result, it will be converted into various products. For example, when fuel gets decomposed, thermally degraded, then the unburnt hydrocarbons and some of the radicals will also be formed. And when oxidizer is decomposed, it will be the ammonium perchlorate will be converted to ammonia and SClO4, and provided the chamber pressure is greater than 1.9 megapascals. If it is lower, it may not really decompose, and it will be giving rise to certain amount of heat, and they will be reacting with each other because the fuel and oxidizer, they will be mixed all together. So, therefore, it is forming a ammonium perchlorate flame or the monopropellant, because fuel and oxidizer are already together and being decomposed from the ammonium perchlorate crystal. And it can give you the temperature of something 1400, sometimes 1300 to 1400 Kelvin, it gives temperature. This is your flame. And beside this decomposed product of the ammonium perchlorate will be also diffusing towards that without really reacting, and also mixed with the decomposition products of the fuel, and then a flame is formed at the interface of this ammonium perchlorate crystal and binder, that is known as the primary diffusion flame. And keep in mind that in premix it is really already mixed together, but in this case both the fuel and the oxidizer emanated from the decomposition of ammonium perchlorate and mixed at the interface of the diffusion flame. And as I told that this will be oxidizer rich, the composition decomposition of ammonium perchlorate will be giving you oxidizer each product. Therefore, all oxidizer will not be consumed in the ammonium perchlorate flame, and it will be going beyond it, it will be traveling that. This is your oxidizer. And again the products, some of the products also will be moving towards that diffusing, it will be diffusing toward that also. So, these are the fuel products, right, which will be moving towards that, and when they will come in contact with the oxidizer, a flame is being formed, and that is the final diffusion flame. So, as I told earlier that primary diffusion flame, which will be occurring at the interface between the ammonium perchlorate and binder, it will be giving a combustion products, and the temperature what you can achieve in this case, it is something 2800 Kelvin of this flame. This is the flame. Okay. The final diffusion flame can be formed when the ammonia is reacting with the unburnt hydrocarbon and also HCl4 and giving to the combustion product, and that temperature could be around something 3200 Kelvin. This is the temperature what we get. And keep in mind that this will be dependent on the chamber pressure. As I told, if the pressure is low, then the time required for the complete combustion of the other chemical reactions will be quite slow as compared to the diffusion time. So, therefore, the premix combustion will be predominant. That means, at low pressure the regression rate or the burning rate is controlled by premix flame. But at the high pressure the time residence time required for the combustion to occur will be controlled by the diffusion process, because at high pressure the chemical reaction will be occurring very fast. So, therefore, at high pressure regression rate is controlled by diffusion flame. Keep in mind that although we have shown the flame in an exaggerated manner, it is taking a very larger spatial domain, but note that the thickness of the flame will be order of some few mm, and that thickness, like if you look at this, is I can say the thickness of the flame will be decreasing when the pressure of the chamber increases, and it is a quite complex in nature, and therefore, it is not really possible to discuss in this class. However, it is very essential know to the regression rate, and if some of you are interested, you can look at this paper to find out how the regression rate can be being obtained by using analytical model. And but keep in mind that the burning rate is important parameter which must be known, so that for designing a rocket engine, also learning about how it will be operated and its performance. So, therefore, we need to really know the burning rate of the propellant. So, question arises, how can we measure the regression rate of propellant? Of course, one can predict the burning rate or the regression rate of propellant, but measurement is very important. So, what are the ways by we can measure the burning rate of propellant? Of course, it is very easy. If you can say that if you take any solid fuel and you can look at how does the regressive surface or the burning surface is receding with respect to time. So, then you can get, but in case of solid propellant rocket engine, the propellant has to be burnt at high pressure. We know why we are using high pressure in the rocket engine. Therefore, it is obvious that the burning rate must be also changing with respect to the chamber pressure, and so also the propellant temperature. Now, question arises, how we will determine the regression rate of the propellant experimentally. So, there are three methods are being used routinely. One is standard strand or the Crawford burner, and other is the small ballistic evaluation motor, the other one is full scale rocket motor or the motor. Keep in mind that in the third case, which will give you the actual situation and it can simulate the actual condition, such that whatever the regression rate you will be getting will be the right one. But however, it is a very costly affair and quite complex in nature, and also quite risky in doing that. Therefore, people have devised a small evaluation rocket engines so that they can do, but the scaling is a big problem in that. But however, you will be more realistic as compared to the strand or the Crawford burner. But Crawford burner or the strand burner is being used very much whenever one is developing the propellant for a certain application, and so that you will be changing your composition and looking at how these changes is affecting the regression rate at different pressure. So, let us now look at a schematic of a strand burner, and so that is shown here in this case. If you look at, this is your propellant strand, which is being shown here in this burner, and this is a generally a cylindrical grain which is being manufactured with certain diameter and certain length, and this has to be having a liner or the inhibitor which will be acting as a inhibitor kind of things, so that it will be not reacting with the propellant, or it will not get affected by the propellant, it will be bonded properly. And beside this, the insulator will be there, which will be arresting the heat which will be transferred due to the ignition. This is your ignition wire or ignition coil, which is being placed on the surface, and when the heat is transferred to this, and then heat should not go transfer, so that the heat transfer to will be almost 0. And keep in mind that this can be connected, and then this thing, and this whole propellant is being housed in a holder, or is being clamped into a holder, so that it will remain perpendicular and it should not affect during its operation. And whole this propellant strand along with the propellant holder are placed on a chamber. This is your pressure chamber, in which you can change the pressure by using the nitrogen gas or any other inert gas, and this gas has to be filled to start with the help of pressure regulating valve, controlling valve and ball valves, so that you fill this chamber pressure. And there is another surge tank is being used, just such that whenever this propellant is getting burnt, whenever this propellant is getting burnt, and this will be releasing certain amount of mass, so that the pressure of the chamber will be increasing. Then you cannot really keep constant this pressure in during the experiment. So, in order to take care of that, a surge tank, which is a very huge tank being used, such that the small mass getting released due to this burning of propellant, it will not when the small amount of propellant is converted into the gas, it will not really increase the chamber pressure. So, generally certain wires being embedded here, certain wires is being embedded beforehand, so that like nickel wire or some at equal distance or known distance, this distance will be known, or the length, this distance, if I say this is L1, this total is L. So, then it should be known. And then of course, whenever this combustion front, if I say this is your combustion front, which is coming over here, this is your combustion front. different, whenever it will be coming in contact with this nickel wire or any other metal wire which can be melted easily, that will give a signal, and with the help of chronometer you can find out the time, and you can find out a regression rate very easily, that is r dot is equal to the length divided by time, that will give me the regression rate or the burning rate. And that is the older method which is being used, but in recent time there are several other methods which is being devised. These are the methods of measurements, like one is the ultrasound wave which is being used to find out how much length of the propellant being regressed with respect to time. So, also the optical method, and when you do that you will get the data of basically the regression rate with respect to chamber pressure. I can plot this ln r dot with ln p c. So, you can get something data over here. So, you can plot this thing and you will get a relationship that is basically r dot is equal to a p c. If I consider this as a slope of this is the slope, slope will be really the n, that is this n, and a will give me intercept, and this is basically ln a. From this I can get this ln a, and I can get a relationship. This is a semi or empirical relationship, and interestingly you will find that this relationship can be valid for both double base propellant and also the composite propellant. And keep in mind that n is known as the pressure or the combustion index, and a is not a non-dimensional number, it is having certain dimension, and this is known as temperature coefficient, and this n will indicate the extent of the chamber pressure that can affect the regression rate. And keep in mind that a is basically not a constant, it will be dependent on the temperature, and keep in mind that this relationship is known as the Wallace law, or it is also known as St. Robert's law in literature. It is not a law, but people are using. This is basically a empirical relationship which is valid for certain kind of propellants. And as I was telling that a is not really constant, a is basically a which is a constant and divided by T I minus T p. T I is your ignition temperature, or it is known as self ignition temperature of the propellant, and T p is the propellant temperature, which is similar to the ambient temperature of that region where it is being operated. Keep in mind that the burning rate data in this burner is generally will be lower by 4 to 12% as compared to the actual full scale motor, but however, this can be utilized as it is very easier to conduct experiment and get the data. So, with this we will stop over, we will be discussing about this Wallace law or the St. Robert law for the regression rate in the next lecture, and thank you very much.